So far, we've learned about chemical reactions, which involve interactions between the electrons of atoms. But those reactions don't change the number of protons or neutrons in an atom. Nuclear reactions, however, are reactions between particles that result in changes in the nucleus of an atom. The atoms can actually change their number of protons, which changes the identity of the atoms involved. There are two general types of nuclear reactions: fission and fusion. Fission reactions occur when an atom is split into multiple particles. You can identify a reaction as fission when the nuclei of the products are smaller in mass than the nucleus of the original atom. Fission can be triggered by firing a particle as small as a neutron at a large, unstable nucleus. The neutron, even though it's so small, deforms the nucleus just enough to allow the repulsive forces between the protons in the nucleus to break the nucleus apart. This break produces smaller nuclei and other free neutrons that move away from each other at great speeds. Not all atoms are fissionable. The most common fuel for fission reactions is uranium-235, which is less common than other types of uranium. Plutonium-239 is another common fuel for fission reactions. In order to fission, the nucleus must be relatively unstable in the first place, before it's struck with a neutron. Because fission reactions emit free neutrons traveling at great speeds, these neutrons can collide with other large nuclei in a sample and lead to other fission reactions. This leads to a fission chain reaction. And while one isolated fission reaction does release a large amount of energy, it's this chain reaction effect that's able to power nuclear weapons and nuclear power plants. The atomic bomb is a fission weapon. Inside the bomb, a neutron is fired at a sample of uranium-235 or plutonium, which starts a fission reaction. That initial fission reaction frees more neutrons, which collide with other atoms, creating more and more fissions in those nuclei. The fission chain reaction builds pressure and temperature inside the bomb until it eventually explodes. This was the process used to power the atomic bombs Fat Man and Little Boy that were used at the end of World War II. Fission chain reactions are also used in nuclear power plants. Nuclear power plants provide a significant amount of the world's electricity. These power plants use a controlled fission chain reaction to heat water and produce steam that turns a turbine to generate electricity. Unlike the fission chain reaction that takes place inside an atomic bomb, the chain reaction in a nuclear power plant can be controlled in two ways. The first is through neutron absorption, which uses a device to absorb some of the free neutrons to prevent them from producing too many fission reactions. The second way to control a fission chain reaction is by neutron moderation, which uses water or carbon to slow down the neutrons in a chain reaction so they're not traveling too fast. This allows nuclear power plants to produce electricity in a way that's more safe and efficient. Even so, the process of fission produces radioactive waste that must be contained and disposed of. This waste can be dangerous and expensive to manage. When we write the equations for nuclear reactions, they look like this. The elements are written in isotopic form. The superscript to the left of the symbol tells us the mass number, protons plus neutrons, and the subscript to the bottom left tells us the atomic number, or the number of protons. The isotopic form for a neutron has a mass number of 1 and an atomic number of 0, since a neutron has 0 protons. In a fission reaction, all the products have smaller mass numbers than the original atom. When you write the equation for a nuclear reaction, all of the mass numbers on the reactant side should add together to equal the total of the mass numbers on the product side. The same is true of the atomic numbers. They should add up to equal the same number of protons on both sides of the equation. The other type of nuclear reaction is called fusion. Fusion takes place when two atoms or particles come together and fuse into a single larger particle. Fusion can release up to 10 times more electricity than fission, which would make it great for producing electricity in nuclear power plants. But it takes a large amount of heat energy to get a fusion reaction started. So scientists have not yet found an efficient way to use fusion for energy production. The challenge is finding a way to get more energy out of the process than you have to put into it to get it started. Part of what makes the fusion reaction so attractive as a source of energy is that it produces less waste than fission. So, if nuclear power plants could be powered by fusion instead of fission, there would be less radioactive waste to dispose of. But until the fusion process can be made more efficient, fission will need to continue to be used in nuclear power plants. The most common place for the process of fusion is on the surface of stars. Stars form as clouds of hydrogen gas pulled together by gravity. As the cloud is pulled together, it becomes more and more dense, and the pressure and temperature rise. When the temperature is high enough, hydrogen nuclei start to fuse together to form helium. After the process of fusion begins, the star begins to glow. The light that we see from stars is part of the energy that's released in the fusion reaction. As a star gets older, the nuclei getting fused together get heavier. The heaviest atom that can be created by fusion on stars is iron. If a star is large enough when it dies, it will supernova, creating a huge explosion. The force and heat from a supernova is great enough to fuse together large nuclei to make elements heavier than iron. All elements with an atomic number greater than that of iron were formed in a supernova explosion. The fusion process has also been weaponized. The hydrogen bomb, or thermonuclear weapons, use the process of fusion. But since fusion takes a great deal of heat to trigger, these weapons actually start with a fission reaction. The first stage of fission produces enough heat to trigger the second stage of fusion. Since fusion releases more energy than fission, these weapons have the potential to be very destructive. The equation for a fusion reaction also uses the isotopic form of an element. We can recognize this equation represents fusion because the mass number of the products is greater than the mass numbers of any of the reactants. We can also add the mass numbers of the reactants, and they should equal the sum of the mass numbers of the products. The sum of the atomic numbers should be equal for the reactants and products as well. The reactions of fission and fusion are both nuclear, meaning they involve a change in the number of protons in an atom's nucleus. They both also produce large amounts of energy, and this makes them important processes for us to understand and harness. Thanks for listening.